So I'll be presenting my research update on using autonomous rendezvous transformer for trajectory optimization. So with special emphasis on trajectory generation. Yeah. So these are the contents that I'll be covering today. So I'll start off with the motivation. I'll be talking about the genetic algorithm, which is the technique which I'm using for generating the trajectories. I'll be testing it with the art pipeline, and I'll be talking about some of the passive safety results going forward. All right, so let's get started. So, so we essentially want a good spacecraft guidance in the presence of a lot of constraints. So you have a lot of operational constraints, you have passive safety constraints, and so forth. And we need this for two objectives. We need it for general mission design, and we also need it for onboard autonomy. So these are the two things that we are targeting. And the common thing between both of them is that the solution space is highly non-convex with a lot of multimodal solution spaces. Specifically for general space mission design, you need some kind of trade-off space analysis. You want to see how different competing objectives are modeled, and with specific missions, you need like specific you need specific trade-offs. So you want to have a good understanding of the entire trade-off space. And with regard to onboard autonomy, you want to have reasonably low computational complexity because you want to autonomously, quickly compute the trajectories for whatever dynamic obstacles you encounter and other situations you encounter. So, but the main thing is the main similarity between all these things is that the solution space is highly non-convex, and we need like a suitable solver for finding a global minima in this highly non-convex space. So there have been many solvers proposed before. So some of them do the convexification of the problem, and then there are standard solvers like SCP. You have nonlinear programming solvers. You also have heuristic solvers which consider the entire solution space, and you also have some gradient-based algorithms. So most of these solvers usually require reasonable initial guesses for doing it. There are also some sampling-based algorithms which may not need initial guesses, but then you might be sacrificing on the computational complexity, or sometimes like you might not get a good indication of the trade-off space. So these are some of the things that have been done before. So if you see many of these things in the many of the solutions proposed in the past, they consider HCW dynamics. They incorporate passive safety. Some of them are sampling based. There are many methods, but one thing is that they don't consider the trade-off analysis. So it's like if you have very specific mission design where you want to know where you have a lot of competing objectives, these proposed methods do not necessarily consider all of that. It just like kind of returns one of the solutions. And there have been some new methods which do consider multiple objectives. Like the most recent one over here considers multiple objectives, but it is like not specific for orbital astrodynamics. It's very generalized to MTPs. And Slab has also been working on something very similar, which is the autonomous rendezvous transformer, which is specific for which can be made specific for orbital mechanics, and which is what I'll be talking about. So overall, the thing is we want well-learned initial guesses. That's like one of the common things which we saw in the non-convex solvers. The quality of the initial guess definitely influences the solution that the solver returns. So this is one of the proposed methodologies where you're supplying like a reward to go and constraint to go parameters which denote which is an indication of the objective functions. So you like the reward to go is an indication of what is the like the fuel cost, that what is the expected fuel cost which this trajectory is going to encounter, whereas the constraint to go is an indication of how safe this trajectory is going to be. So upon passing that an initial state, this transformer returns an expected action, which is then again optimized to give a more specific action, and then this is done auto-regressively for multiple time steps until you get the entire trajectory. So so what we do is we have this auto-regressive inference. We have some initial conditions, and upon your feeding that to art and you giving specific reward to go and constraint to go, you get some initial guess. And this initial guess is passed on to the standard non-convex solvers like SCP, which then returns an optimal solution. And the reason why we are kind of passing these additional performance metrics like reward to go, constraint to go, is because we want to capture the trade-off space, which is what some of the solvers, some of the papers earlier didn't consider. So the aim is we perform machine learning and we try to make art generate a really good initial guess so that the SCP solvers can quickly converge to the optimal solution, which is hopefully the global optimum. So the thing is, in order to generate a very good initial guess, we need to leverage the pre-processing. We need very high quality data for training art, preferably the ones which are globally optimum for the given trade-off metrics. So one of the things which determines the trajectory quality is the algorithms that consider the entire solution landscape so that it can capture all the global minima which is out there. And another thing way in which we can target, diverse regions in the trade-off space with like competing fuel, time of flight, safety, and other scenarios is to perform some kind of multi-objective optimization. So, and one of the algorithms which considers both the entire solution landscape and like multiple objectives is the genetic algorithm, which is what we have been using for generating all the training data. So I'll just quickly talk about that. So this is inspired from evolution, where only the fittest individuals survive. So you essentially start off with an initial population of chromosomes, which have some kind of fitness levels associated with them, and only the most fit chromosomes cross over and they reproduce and they create new chromosomes, which then form the next population. So so essentially, the hope is that through multiple generations, you're evaluating the fitness of the chromosomes, and the chromosomes are the representation of the most optimal solutions. So as you go throughout the generations, the hope is that you're leading to more and more optimal solutions because only the best traits are being carried forward by the chromosomes. So, and GA is not new to astrodynamics. Many papers in the past have been considering it. It started with like simple two-body dynamics, verifying commonly known orbit transfers. And earlier it was just like a single objective. And going and moving forward, there have been like multi-objective considerations, and people have looked at trajectory robustness. They have also considered passive safety, and they have modeled the chromosomes in different ways. So and towards the end, there are also been some papers which were used for like targeting optimal satellite constellations and so forth. So GA has been extensively used in this field. And so one of the examples that I'll be considering throughout this presentation is going to be this low Earth orbit scenario with these parameters. So these are the chief orbital elements, and this is the initial relative orbital element in the RTN space for the deputy, and these four denote the final positions in the RTN space that the deputy needs to reach. And this represents the randomization of the initial conditions about this point. So this is the standard mission that I'll be considering throughout. So let's try to understand what GA is exactly trying to do. So initially you have this optimal control problem. You have the two of the main objectives that we need to be concerned about are time of flight and the fuel cost. And we wanted to satisfy a lot of constraints, and the main ones are the dynamic constraints. You may also have certain boundary conditions. You wanted to go through certain waypoints, and you wanted to make sure that the trajectories are safe and it doesn't collide. And when you translate this into a genetic algorithm problem, you finally get you're trying to model this optimal control problem by creating this particular chromosome, which is a representation of the trajectories, and these conditions, this objective and some of these conditions become fitness objectives. So the thing is, in for genetic algorithm, the chromosomes are the representation of the best solutions. So, and we want to make sure that we get the most fit chromosomes. So TOF, delta V, and passive safety becomes fitness objectives for the genetic algorithm. And so I'll just quickly go through the workflow of how GA exactly works. So you start off with some initial conditions, some final conditions. And once you choose that, you create a set of population, you create a set of chromosomes. And then following the logic of GA, you try to evaluate the fitness on multiple criteria, which are the multiple objectives. So you want the solutions to have limited time of flight, you want it to have low fuel cost, and you want it to be passively safe. So these are the three objectives that the GA is considering. And once you consider that, once you evaluate the fitness levels of all the chromosomes that you consider, you choose the best individuals, you do the crossover, mutation, etc., and then you end up with a new population. And then this repeats throughout, and then you finally end up with some really good trajectories. So let's go one by one and dig into what it means. So, so over here in population creation, so you're creating multiple chromosomes of this structure. So TF is basically the time of flight of the trajectory. These X's denote the waypoints that the trajectory needs to go through, and the delta K is a representation of when it needs to go through those respective waypoints. So so each chromosome denotes these aspects of the trajectory. It still doesn't know this. The chromosomes do not encode the states or the actions. It only tells the final time of flight and the waypoints it needs to go through. And once you create that, we go into the fitness evaluation. As you can see, the TF is already there in the chromosome, so the time of flight can be inferred directly. And so let's discuss the next component, which is trying to identify the fuel cost based on this chromosome. So you end up with a constraint optimization, and I think this is one of the advantages of GA because it's kind of stripping away the non-convex part of the problem, and you end up with a convex optimization problem. So when you're evaluating the chromosome, which already captures the non-convexity, you're left out with the things which are either affine or convex. So dynamics and waypoints, you have both of them are affine, and over here you have a convex function. And therefore, the second fitness evaluation becomes a convex optimization problem. So that makes it very, very convenient. And going to the next one, which is the passive safety. So essentially you have some keep out zones that you do not want the trajectories to go next to. And basically this flowchart just represents how we can quantify the level of passive safety which is there in the trajectory. So you model the KOZ, you get this matrix, and you do the stochastic propagation, and we're using chance constraints to quantify passive safety. And finally, after all of this, you are left with a constrained residual, which is an indication of the level of passive safety which is there in the trajectory. So what we do is, so what happens is that once we evaluate the delta V fitness of the chromosome, we compute we compute the residual fitness of, we try to compute the residual fitness of all the trajectories which are possible as all free drift states from any point in the trajectory. So like you take so each chromosome is a representation of one trajectory. You take all possible states in the trajectory, and you perform a free drift from all possible points. And once you do the free drift, you see what is the maximum residual that you get when the free drift happens. How basically it's an indication of how close it goes to the keep out zones. And once you accumulate all of that for all the free states, you apply a suitable penalty function, and you get the fitness evaluation in terms of passive safety for the new chromosome. So this is like so yeah, now let's move to like validating GA to see like if it's really working out for like well-known scenarios. So GA can be applied for situations involving multiple objectives. So we first start off with verifying if at all it really works for two objectives. And these are like some of the well-known solutions which where like you only perturb one of the orbital elements and you're seeing how the trajectories are. So this is just like one example where you like the delta A is varied, like you have this is the initial and final ROE. And so this particular initial condition generates like a Pareto trade-off, the Pareto front of solutions in the trade-off space. So and this is just a representation of one of the solutions among these solutions. And you can see how it is for this particular scenario. And so this was done for multiple ones. This is for when there is a change in lambda, and this is for when there's a change in EX. Like maybe for instance, over here, you can see that as expected, you can see that the delta A, it first decreases and then it kind of propagates forward and then the delta A increases again. So you can see, you can kind of get a sense of you can kind of get a sense that GA is actually giving the correct solutions through these sanity checks. So yeah, so now this is like one of the examples where, like, I sampled multiple initial conditions and you have multiple trajectories which were generated by the genetic algorithm. So each initial condition corresponds to one Pareto front. So I think, and this is the advantage of GA because you're able to consider the entire trade-off space of solutions. So for instance, you can see like this particular one can correspond to this particular Pareto front, and you can see that there are some nuances, like in case there's like a loop over here, you can see that there is some kind of concavity in this Pareto front. So you can try to like capture a lot of details by generating the training trajectories using GA. You can get a lot of insights from the Pareto fronts in the trade-off space. And this is just another way to like validate it. So you have so the main things to focus right now are like the red squares and the green triangles. So you can see that like when the ROE based GA solutions and the HCW dynamics solutions, they kind of generate the same Pareto front, which is again a sanity check that the GA is working. So now the question is, right now I haven't considered passive safety yet. So right now the two main objectives which we have been dealing with so far are the fuel cost and the time of flight. So the question is, like, would this be enough for getting high quality solutions from art? But so what we do is, we just generate some more training trajectories, which are more specific to the mission objective that we have. And we trained it with around 115,000 trajectories. And the result is it is not that great. So the thing is, since we did not consider passive, it is kind of expected because we did not consider passive safety in the training trajectories. So we do not end up with optimal solutions. You can see that art significantly deviates from CVX and CVX SCP. So and this kind of illustrates the need for passive safety. So so now going forward, I'll talk about how passive safety has been incorporated. And just to again recap, this is the situation that we have. We have this is like the mission objective. This is the chromosome structure that we're dealing with, and these are the fitness values. And these are some of the results that we get. So so this is you get a 3D Pareto front of solutions because you're considering three objectives over here. And these results are kind of as expected. Over here, the main thing which we need is a suitable Pareto front between the fuel costs and the time of flight. Passive safety is kind of more binary, so it's not like we need a nice looking Pareto front over here. So here you can kind of see that initially all of them were like all over the place, but then now it has kind of converged over here. You can see that there is some kind of Pareto front forming, and also one of the ways in which like we can quantify the Pareto front convergence is by having some kind of reference point far away and then trying to compute the volume, the hypervolume of which includes that reference point and all the points in the Pareto front. And the hope is that like once the hypervolume kind of converges to a high value, that is an indication that the genetic algorithm has converged. And that is what happened. So like all of them successfully converged for all the final RTN positions. But the thing is, even after all of that, even though we obtained a lot of passively safe trajectories, but there are some trajectories which may not be the most optimal trajectories. So as you can see over here, there are some kind of loops over here, and I think this may be because of some of the waypoints, because of like a very bad waypoints heuristics which was used in the initial population. So although the trajectories which were obtained in the end were passively safe, and it was like very far, it was in the Pareto front of solutions which had converged. There is still it is still a little far away from optimal solutions, as can be kind of visually seen from this. And when you compare it with other methods like SCP, you can see that there is still some fundamental issue which is there with GA. So over here, for instance, when I consider passive safety of just like one step of free drift, which is essentially just collision avoidance, you can see that, I mean, it does it does better than SCP because the Pareto front is more closer to the origin than for SCP. But then if you consider like a more extended free drift, then you can see that like some of these solutions are missing because they're not like passively safe. And even after going to up to 500 generations, you don't end up with like reasonably looking solutions. So, and I think that kind of forms the main motivation for the future work as well. I think GA has like a lot of hyperparameters, and maybe fine tuning them is one of the ways in which we can hopefully get better solutions than the SCP. Because the hope is that in the end we use GA to get very high quality training trajectories, which can be indicated by the fact that the Pareto front tries to come within this region, which is just below SCP. So I think that is one of the main things to do. And on the side, there are other things which can be done, like speeding up the inference so that we can do more testing very quickly. And that involves parallelization using different time discretization schemes, etc. So that's about it. Yeah.